right, so in the last video we talked about how we did this process of translation. Again, these are very brief little videos, so it doesn't incorporate everything that goes into this. But right now we're at this stage where we have this nascent protein, this protein that's been synthesized. The last step that we talked about was it being folded up so that the hydrophobic residues are hidden and the positives and negatives are interacting. The positives and positives are pushed away from each other. Now what we're going to do is we're going to talk about post-translationally modifying these proteins so that they can become more or less active. And so post-translational modifications that we're going to talk about are going to be phosphorylation, dephosphorylation, acetylation, deacetylation, ubiquitination, oxidation reduction, and ligand or nucleotide binding. These are the 5 that we're going to talk about as far as this course, because these are the 5 that are most regulated and most important in driving the exercise response that we're going to see physiologically within muscle and other tissues. So what are we talking about when we're talking about these things? So the first thing is phosphorylation, dephosphorylation. This is a phosphate group here. And what you should see is this is a phosphorus with 4 oxygens. 2 of the oxygens are unbound, so it's only got 1 binding site, so they have a negative charge here. So that's a double negative charge. So this is a highly negatively charged group. All right, so that's really, really important. The enzymes that are important in phosphorylation, dephosphorylation are kinases. Kinases are just proteins, and they have the ability to add or to decorate other proteins with phosphates. There's phosphatases. So phosphatases take off the phosphate groups. So they remove the phosphate groups. And therefore, what we can do is if we want to increase, just like we talked about before when we talked about other things that are a balance, like RNA, the amount of RNA in a cell, the amount of how big your muscles are, if we want to increase phosphorylation, we can either increase the activity of a kinase or decrease the activity of a phosphatase. Just like I told you before, if you want to make your bank account bigger, you can either bring in more income or you can decrease the amount that you spend. So if your income stays the same and I decrease the amount that I spend, my bank account gets bigger. Same thing happens here with phosphorylation. If I keep the activity of the kinase the same and I decrease the activity of the phosphatase, I get more phosphorylation, and we're going to see that potentially down the road. All right, so what's the function of a phosphate group? So we talked about how proteins take on a shape based on hydrophobicness, and then we talked about the fact that the positive charge interacts with the negative charge. And so if we have a lot of positive negative charges, if we have a neutral amino acid, that's what we're going to take, is we're going to take tyrosine, we're going to take serine, and we're going to take threonine, which are neutral amino acids, and we're going to add these phosphate groups to them, and we're going to make them negative amino acids. So if you have a neutral and is near a positive charge, if I add a phosphate group, now what it's going to do is it's going to push it away from that positively charged amino acid that it's sitting next to. So when you add a highly negative charge, it's going to change the protein shape and function. And when it does this, it can move it to a different location. So what it does, what phosphorylation and dephosphorylation does, is it can activate or inhibit an enzyme. It can create a new binding site where proteins that didn't bind together before now can bind together. Or it can cause a protein to move to a different location in the cell. And so when we're talking about exercise, the kinases that we're going to talk about over the course of this course is we're going to talk about the AMP activated protein kinase, which is a protein kinase that is activated when we're using ATP faster than we can produce it in our body. And so that's going to be really important for endurance adaptations. We're going to talk about the mammalian or the mechanistic target of rapamycin, complex 1, and that's the protein that we turn on. That's the kinase that we turn on when we do resistance exercise. And that's going to be really important for the resistance exercise and the nutrition components of making your muscle bigger. And then the calcium calmodulin protein kinase, or CAM kinase, that's also important in endurance exercise, because every time we fire our muscle and we cause a contraction, we increase calcium. And if we're going to run for a long period of time, we're always increasing calcium again and again and again. And over that time, calcium concentrations go up, and that activates the calcium calmodulin CAM kinase. All right, so what does a kinase reaction look like? You have a protein here that's in a shape, and that shape is determined by all of these things we talked about. But if you have an area where you have a neutral amino acid here on this little bar, and you take ATP and you use a kinase, that kinase takes ATP and it cuts off the last phosphate off of ATP and it adds it to our protein. and it creates ADP and a phosphorylated protein. And you can see that what's happened is we've moved this bar away from these sheets. So this represents a helix, and these represent sheets within a protein. Those are just protein structures. But you can imagine that there's a positively charged structure here on the sheet, and when you add the negative charge to this tube, basically what happens is that's now forcibly pushed away from the positive charge on the other side. And if this is the active site of an enzyme, now you opened up the active site and the proteins can come in and you can have more activity. The phosphatase just does the reverse. It comes in, cuts off the phosphate group, releases it, and the protein reshapes into the smaller conformation. Whenever I draw, and I'm going to draw a lot of kinase cascades as we go through this course. When I draw them, I draw one thing, activating another thing, activating a third thing. What really happens is almost like what we're seeing with the COVID-19 outbreak, is that one person gets infected, and they infect 3 people, and then very soon they infect another 3 people each, and now what we're talking about is within 4 steps, we've got a huge number of active or phosphorylated proteins. Because if I take if I phosphorylate a kinase and it phosphorylates other proteins and that increases their activity and their kinases, they're going to phosphorylate. And it's this signal amplification. And as you see with the COVID-19 pandemic, what you're seeing is this huge increase in the number of cases very rapidly, exponential growth. That's what happens when we move from one kinase to the next to the next. You amplify this signal and you get even more. You take a very small signal and you can make it into a very big response.